So we already mentioned this in the previous video, and that is that the work done by the weight force, right, the weight or the gravitational force, since the displacement is a little blue box, since the displacement is in this direction and weight acts perpendicular, we know that the work done by weight is equal to, it's just going to be the force mg, right, as a vector, dot d is equal to mg d cosine of the angle between them, which is 90, but cosine of 90 being 0 means that this entire term is 0. Work done by mg is equal to 0, okay? So that's the answer to number 3. Also, remember, intuitively, it makes sense that if you've got a displacement in this direction, that a force that's acting perpendicular has no component either to slow it down or speed it up. That is, to change its kinetic energy in any way. Therefore, it's doing no work. All right? So now we'll go to question number 4. And that is, what is the coefficient of friction between the stuffed monkey and the surface on which it slides? Nobody bothered to ask me why it's a stuffed monkey. You did? Because it's easier to work with boxes than stuffed monkeys? Oh, okay. All right. I was distracted by the stuffed monkey. All right. So how do we find the coefficient of friction? Now, do we need to do anything? Do we need to involve work energy quantities here to find the coefficient of friction? No, I put it on a work energy test because sometimes you just got to be able to say, you know what, that doesn't have anything to do with this, right? You know, you have to be able to look at your toolbox and say, what is it that I have to solve this problem? We know that delta V is equal to 0. We talked about that. I had you circle it on your paper, right? The reason we know that that's true, well, I'm writing a sigma. I don't want to write a delta. My whole Greek alphabet's messed up. All right, so delta V is equal to 0. All right, that means acceleration is equal to 0. That means net force is equal to 0. All right, if we examine the forces, now this is one where we have to consider the vertical again. So we're going to redo our free body diagram. Here's our horizontal, and that's the direction of the displacement, right? So that's the pertinent angle here for finding component in the direction of displacement. We have normal force here, we have tension here, we have mg, which is a little bit bigger this way, and we got friction acting this way, okay? If the net force is equal to 0, that means that the net force in the x direction is equal to 0. And these are the two forces we worked with in the previous problem when we were finding the net work done, or actually the work done by friction, okay? So when we did this, we're going to say that that's in the x direction, we got tx minus friction, okay? That's the net force, and we know net force in the x direction is equal to 0. So again, we're going back to using what here? What is this? We're setting up our two-equation strategy. That's exactly right. How much force do we need? We don't need any because we have 0 acceleration. And where does that force come from? It comes from tx in this direction and friction in this direction. All right. Doing like that, we get x component of tension minus frictional force. This is kinetic friction. I haven't notated that so far, but it is. All right. So then we get tx is equal to kinetic friction. That means that tx, or t cosine theta, theta t, right? That's the angle relative to the horizontal, relative to the x direction, because that's what we're evaluating, is equal to, how do we break friction down? Mu normal force. Okay, so mu kinetic times normal force. Now, normal force is always equal to mg, right? No. Good. All right. So now, since we have normal force, we have to evaluate forces in the y direction as well. So let's go back up here and look at our free body diagram. Looking at this, I'm going to evaluate forces in the y direction in blue. Okay? So let's just come down here, and we can scroll up and see that the forces acting in the y direction are n ty, right? This component right here, ty, and mg acting downward. Okay? So I'll bring those down here, and we'll say that the net force in the y direction is equal to 0, right? How much force do we need? None, because we have 0 acceleration. Net force in the y direction is equal to, in the positive direction, we have normal force. We have ty, good. And in the negative direction, all right, mg acting downward. Putting all those together and solving for n, we get n is equal equal to mg minus ty, or mg minus t sine theta. All right, so now using that normal force, I have a capital N there and a small n here. But let's just take this whole thing right here and group it and clone it and drag it down here. Sounds like a pat it and with a B or whatever that thing is we say. All right, so t cosine theta. All right, so now we got t. Put it and pat it and bake it with a B. Put it in the oven for baking. You guys ever heard of the sponge cake? All right, so that's mu k times normal force. So even though it's small n here, big N here, it's the same thing. This is mu k times mg minus t sine theta is equal to t cosine theta. So now rearranging to solve for mu k. Mu k is equal to t cosine theta divided by the quantity mg minus t sine theta. And this is what hung some of you guys up, is this part right here, while you got the wrong answer. But I gave you 3 points for getting something that was close, but you only got the full 5 points if you recognize that change in the normal force due to the presence of the upward component of the tension force. So solving all the way through and putting all that stuff in your calculator, it actually comes out to be 0.321. I think the answer D on there was 0.319. That's within a couple percent, or maybe even within 1%. It's 2 on 300, so it's within 1%. But basically what happened there was I took t cosine theta. If you do t cosine theta, you get 14, and if you it's 14 point something. So if you just put it in, you get this bigger number. If you put in 14, you get 0.319. Okay? So it's better, once again, it's better to use an expression like we have right here instead of putting in a rounded number like 14 newtons. Okay? So this is what was actually on the paper, and that's choice D. Okay? Any questions?